In chapter 23, we're going to talk about mirrors and lenses. And last chapter, we dealt with them as kind of like an introduction to reflection and refraction. Whenever a ray was being reflected off of a surface, that was a reflective surface. That's what a mirror is. So when we deal with mirrors, we're going to talk about the law of reflection. This diagram right here, it looks crazy. We're not really going to dive into this diagram too much, but these angles are the same, right? So this would be my incident angle, that's my reflected angle. So the law of reflection will hold for mirrors, and we will see how prisms can be shaped to form lenses, and we can use the law of refraction to focus an image in different locations, or see how the light behaves as it passes through a lens. So we're going to talk about mirrors first, so we're going to be dealing with the law of reflection. In chapter 22 we dealt with flat mirrors, right? So this was always true, right? But if we had a ray that was perpendicular to a flat mirror, it reflected right back in the same direction. So with curved mirrors, we still have the law of reflection at all these different points, but the light rays behave a certain way, and sometimes an image is formed. So we're gonna explore what type of image is formed, where it's formed, and describe its properties. So the first mirror we're going to deal with is a concave mirror. Concave mirror. So a concave mirror is shaped like this diagram here, right? If you ever heard the words concave and convex, when you were little, maybe in your science classes when you were younger, I always memorized the concave shape. I always thought about a spoon, right? So this would be like the part of the spoon that you would be holding something in, right? Kind of, it's caved in. All right, so this is a concave mirror, so it's curved like this. So what if we just took a laser beam, right? If we just took a laser beam of just pure white light and we shone it directly at the mirror, what would happen? If it was a flat mirror, it would come right back to us, right? It wouldn't change direction other than being reflected back at us. But with a curved concave mirror, we see the law of reflection happens, but it happens at every point on this mirror. And so if you can think about that laser beam as a whole bunch of parallel rays that are hitting at different points on this surface, the law of reflection occurs, right? Incident reflected, all through the surface of this mirror. But then these rays kind of bounce off in different directions. Where these rays converge, right? And when I say converge, I mean where these rays meet. Okay, where these rays meet is the focal point. It's the focal point of this mirror. Now the focal point is, and we'll talk about this in a later slide, the focal point is half the radius of curvature. All right, so this is how we make mirrors and lenses. So this is curved, right? But if we continued this path, right? If we continued this surface, and we can make it a circle, right? So this is a curved mirror, but it's shaped like a portion of a circle, and so it would travel around like this, and it would make a large circle, and then the center would be like here somewhere, right? And the distance from that center, from that point to any surface on the mirror, or any point on the mirror surface, is the radius of curvature, right? So it's basically the radius of the circle. And so we make mirrors and lenses with a certain radius of curvature, so we can determine the focal point, because the focal point is always half the radius of curvature. And again, we'll get into that a little bit more if we're asked to calculate that or something. But that's how we make our lenses and mirrors, with a set focal point. Okay, so the focal point, or the focal length, I'll refer to it as both throughout the video. So the focal point, or the focal length, is always constant for a mirror, right? It's a property of the shape of this mirror. And if we had a bunch of parallel rays from some source really far away, they would converge here at the focal point. So we've got a bunch of different rays, but I don't want to draw a ton of rays, right? If I want to kind of draw a picture of what's going on, I don't want to draw a ton of rays and clutter up my diagram. So this is what's referred to as a ray diagram. We like to use 3 principal rays when we're drawing a ray diagram. So one of our labs, one of the exercises is drawing a ray diagram based on an object's location. So we usually draw our object like an arrow, right? An upright arrow. Because typically, you know, we've got an object, you see this vial of some liquid, it's in front of the mirror. So it's upright, right? It's upright right now, and it's in front of the mirror. So we're going to draw 3 principal rays. 3 principal rays. The first ray is going to come from the top of the arrow, and it's going to run parallel to this surface, right? If this is a table or a floor or something like that. So it's going to run parallel to that surface, and then it's going to strike the mirror. And then we've got a law of reflection here. Okay. Now this first ray is a parallel ray, right? First ray is a parallel ray, and it's going to reflect, and it's passing through the focal point of the mirror. Okay, so we want it to run parallel, pass through the focal point of the mirror. The second principal ray, we want to draw it so it travels through the focal point first. So it's always coming from the top of the object. We're going to draw it down at an angle to where it passes through the focal point. When it hits the mirror, we're going to have reflection here again, and it's going to bounce back, and it's going to be parallel to the surface. Okay, so ray 1 starts parallel, passes through the focal point. Ray 2 passes through the focal point first, then reflects back parallel. Now this is usually enough. For this type of scenario, this is usually enough to where we can draw our image. But we're going to draw a third ray, okay, and that third ray is going to pass through what I refer to as the radius of curvature. So this point C right here is the center of the circle that would be formed by this mirror, right, if it was a complete circle. So it's going to pass through the radius of curvature. Remember, this point is twice as far away from the mirror as the focal point. Right? So it passes through that, and what actually happens is it bounces back in the opposite direction. Right? So we still have reflection here, but there's no incident angle, so there's no reflected angle, so it comes right back. All right? So now we've got our 3 principal rays. Where those 3 rays converge is where our image is formed. And see this arrow, it's upside down and it's small. That is the image. Okay, so we've got O for object, I for image. So where is this image? Well, it's going to be somewhere between the object and the mirror. So it's actually being projected in front of the mirror. Okay, it's upside down, right? It's upside down. So we call that inverted. Okay, so the image is inverted. It's smaller, right? It looks smaller from the surface down to where the rays converge. It's smaller than the object. Okay. It's also what we call a real image. A real image is formed when the 3 principal rays actually converge. Okay, so the rays are reflected from the mirror. They meet at some location, and those rays converge. They form a real image. So this picture right here is what we would see, right? So this object is outside the focal length, right? See how it's farther away from the mirror than the focal point? So it's outside the focal point. We've got a real image. It's inverted, and this diagram, it's not much smaller, but in our cases we're going to have a smaller image, and we'll find out how we calculate the magnification, right? How much larger an image is or how much smaller it is. So this is case one. We've got an object outside the focal point. We draw 3 principal rays. This is good practice. All right, we won't be asked to do ray diagrams too often, but it's still good practice to kind of double check our image formation, right? All the properties of this image. So it's going to be real. The rays actually converge. It's going to be inverted, upside down, and it's going to be smaller or reduced in size. Okay, so anytime the object is outside the focal point for a concave spherical mirror, this is what happens: real, inverted, and reduced. So we're going to have a lot of these rules, right? So this is how I want to categorize an image. Okay, real, inverted, reduced in size. So now we're going to take that same object and we're going to move it forward. We're going to take this object, we're going to slide it across the surface, slide it, right? This whole time we're going to get a real, inverted, and smaller image. The whole time the object is outside the focal point. All right? And something happens when it hits the focal point. We won't talk about that right this second, but we're going to pass through the focal point, and then we're going to put the object between the focal point and the mirror. So we're going to try to draw our 3 principal rays again. Our first principal ray runs parallel, and then it reflects back through the focal point. Good. But it's going back through the object, so that's kind of weird. Our second one is going to, it can't pass through the focal point first. Okay, it can't pass through the focal point first, but we're going to draw it like it's coming from the focal point, right? So here's F. We're going to draw a line from the focal point through the top of the image, and then it hits the mirror. Then it bounces back parallel. Our third principal ray goes through the radius of curvature, or goes through the center of our circle, okay, and it touches the top. Notice these rays will never converge. I'm going to draw them, and they're going to keep going in this direction. They're never going to meet on the same side of the mirror. So a real image is not formed in this case because our rays never converge. But if you were standing behind the image, or the object, excuse me, if you were standing behind object O back here, where would it look like these rays were coming from? I would still see these rays if I was behind the object. So where does it look like these rays are coming from? If I take these rays and I draw them back through the mirror, they do look like they're coming from some source inside the mirror. So while the rays don't actually converge over here, they appear to be coming from some source on this side, right? If we continue to draw our lines, that's what these dotted lines are for. Continue to draw those principal rays on the other side of the mirror, they look like they're coming from here. So there is an image being formed, and it looks like it's inside the mirror. But that's what we call a virtual image. So a real image are where rays converge. A virtual image is where rays don't converge on this side of the mirror, but they appear to be coming from a source inside the mirror. It also looks upright. Okay, so it's not upside down, it's right side up, it's upright. And it's larger. So everything is the opposite, right? When the object was outside the spherical mirror, the image was real, upside down or inverted, and smaller or reduced in size. When we move that object in between the focal point and the mirror, all 3 of those properties change. The real image becomes virtual, it's now upright, it's now right side up, and it's larger. Okay, so here are my 2 cases. Here are my 2 cases for a concave spherical mirror. Alright, so I should be able to, if I knew the focal point, or if I knew the focal length, and I knew the distance the object was from the mirror, I should be able to categorize the image. Right? So if the object distance was greater than the focal point, and I was dealing with a concave mirror, this is what I would be dealing with. This is the type of image that would be formed. If my object distance was smaller than the focal length, I would have this type of scenario, a virtual upright enlarged image. Okay. So now let's talk about convex spherical mirrors. Convex spherical mirrors. So we've got our parallel rays, we've got reflection, the same thing, but the rays never converge on the other side of the mirror. If you notice that no matter where this object is, if I try and draw ray diagrams, they're always going to bounce, the rays are always going to bounce away from one another, right? It doesn't look like they're ever going to meet, okay? Now, we still have the same focal length, right? Same focal length. So it is technically over here, right? There's a focal point here and a focal point here, but we're primarily concerned with the focal point that looks like it's inside the mirror, okay? Rays will always appear to be coming from that point there, okay? If we're dealing with all parallel rays, that's what happens, right? These reflected rays all look like they're coming from some location inside the mirror. And this plays an important part too. We've got sign convention when we actually start talking about the math and the formulas and stuff. We've got to deal with distances with respect to either side of the mirror, right? So this focal point is on this side of a concave mirror. This focal point is on this side. Technically, focal length is a scalar, so I mean there's a focal point here and a focal point here, but when we start doing the math and stuff in a couple slides, we have to use positive and negative signs depending on what side of the mirror we're dealing with, okay? So our first case for a convex spherical mirror, the object is farther away than the focal point, okay? If you notice from this diagram, we're like, here's the focal length, so I guess another focal point would be like right here or something, okay? So the object, all right, so the object is out here. We draw our ray diagram, right? Our three principal rays. Here comes ray 1, it's parallel, it bounces, diverges, okay? Ray 2, we want it to run through the focal point, but it can't run through this focal point. It's got to run through this one. So we're going to draw it as if it can pass through the focal point on the other side of the mirror. Now it hits the mirror and then it runs back parallel. So it doesn't actually pass through the mirror, but we're drawing it like it can, right? And then it's going to reflect, it's going to bounce back parallel. Third ray goes through the center, okay, goes through point C. It can't do it, just like ray 2, so it's going to bounce back 180 degrees from its original direction, right? No incident angle, no reflected angle. So these rays appear, they don't converge on this side like a concave mirror, but they appear to be coming from, or they appear to be converging inside the mirror, right? So the rays aren't actually converging, but they appear to be intersecting here, okay? And that's where our image is formed. So it's virtual because the rays aren't actually converging, but it's upright. It's upright. It's not upside down. So the rays converge above this axis, so it's upright, and it's smaller. And that happens regardless of the object's position with respect to the focal point, right? So the object can be anywhere. So that's good. We only have to deal with one case for convex spherical mirrors. We had two cases for a concave, but now we only have to deal with one case for a convex spherical mirror. So that's good. So it doesn't matter where our object is. This is what our ray diagram is always going to look like. We're always going to get a virtual image. It's going to be right side up, and it's going to be smaller. So now we have to talk about the image formation by the mirror in terms of our physical values. Now, some textbooks use different notation, but the most common is this here. So we use the lowercase p, the variable p, for the object distance. So that's how far the object is from the surface of the mirror. Lowercase q is going to be the distance the image is formed from the mirror. And then lowercase f is our focal length. So this formula is very nice because we can use it for thin lenses as well. Okay, so this formula is applicable to our mirrors and our lenses. Okay, so the most common problems is, you have an object, distance, you have a focal length, you have to find where the image is formed, something like that, right? Or maybe backwards, right? You're given the object and image distance, you find the focal length, or you're given the image distance and focal length, find where the object is, something like that. On top of that, we have to go back and we have to use these values to identify what type of situation are we dealing with, right? So what is the relationship between the object distance and the image distance, or the object distance and the focal length, right? Is it outside the focal length? Is it a concave mirror, right? So we have to know all these rules as far as how an image is formed based on the type of mirror and the relationship between the object distance and the focal point. And so what will happen is, like, when we have this information and we do the algebra, we solve this for whatever's missing, we'll get a sign and we'll get a value for whatever that missing variable is, and that'll kind of help us categorize what's going on here. So we talked about an image being larger or smaller than an object. We call that the magnification. Now this is h prime over h. Now what this means is this is the height of the image divided by the height of the object. So it's a ratio of the image size to the object size. Now we used h prime and h here, right? And so this is a consequence of like some pretty heavy geometry and trig and stuff like that. But the magnification formula that we're going to use is derived from that relationship, the h prime and the h, right? So you see that there are like right triangles here, right? So there's an object distance, there's a height, there's an image distance, and there's an h prime, right? So they're right triangles, and so we're using that property to establish this relationship. Okay, so the magnification is negative q over p, where q is the image distance, p is the object distance. So we should already know whether it's smaller or larger. The magnification number is going to tell us two things: how much larger or smaller the image is from the object, and whether it's upside down or it's right side up. So this negative sign is here always, right? So if q is positive and p is positive, then our magnification will be negative. If q is negative, p is positive, our magnification will be positive, right? So a positive magnification means it's upright. A negative magnification means it's upside down. But this ratio, the absolute value, q over p, tells me whether it's smaller or larger. So if q over p is between 0 and 1, the image is smaller. If q over p is greater than 1, the image is larger. So these are basically our two formulas. I've got another table that deals with the sign convention. Okay, so we might have to give different distances or lengths, negative signs, depending on what side of the mirror we're on. Okay. So here is our sign convention for the mirrors. Okay, so it's a good idea to keep this handy while we're going through our problems. Okay, so if the object is in front of the mirror, okay, if the object is in front of the mirror, that's what we're going to be dealing with like 9 times out of 10. We've got an object in front of the mirror, which is basically the left side. The way we've been drawing our diagrams is in front of the mirror is on the left side. Okay, that value is positive. Okay, so if it's on the left side of the mirror, object distance is positive. Same thing with the image. Okay, if we get a positive q back, that tells me that the image is in front of the mirror. Okay, the image is in front of the mirror if q is positive. If it's in front of the mirror, that means the rays are converging. It's a real image, so that's what happens when we get a positive q. We don't deal with this too often, right? But if the object location is on the other side of the mirror, P will be negative. We saw in the case of the convex mirror and the second case of the concave mirror that we had a virtual image that was formed on the opposite side of the mirror. So we had a virtual image formed on the opposite side of the mirror. That is when Q is negative. Okay, so something on the right side of the mirror is negative, something on the left side is positive. Okay. Let's talk about the focal length and the radius of curvature. I talked about the focal length being on the left side for a concave mirror. Let me go back to that picture. Okay. Focal length is drawn on this side of the mirror. So F is positive. Alright. And if we're dealing with a convex mirror, the focal point or the focal length is negative. Alright. So positive focal length, concave mirror, negative focal length, convex mirror. And that's what this says right here. Okay. So basically for mirrors, if something's on the left side it's positive, if something is on the right it's negative. Alright. And the focal length is positive for a concave mirror and it's negative for a convex mirror. Like I said in the last slide, if the image is upright, magnification will come back positive. If the image is upside down or inverted, the magnification will come back negative. And that will depend on the signs of P and Q, because magnification is negative Q over P. Alright, so it depends on the object distance and the image distance signs. Okay. So this is another diagram or another table of signs. It basically says the same here. We're using positive and negative signs. So if this is easier to read, feel free to use this. So I've got basically all three scenarios rolled into one here. Okay. So I've got a concave mirror with a focal length of 10 centimeters. Remember, the focal length is an inherent property of the mirror. That's how we make them. So I am looking for the image distance, looking for the magnification, and then I want to describe the image. Is it real or virtual? Is it upright or inverted? And is it larger and smaller? For the three following object distances. So I'm going to deal with three different scenarios for a concave mirror. So three different object distances, 25 centimeters, 10 centimeters, 5 centimeters. So that's three different examples I'm going to do. I'm going to categorize all the images, whether they're real or virtual, upright or inverted, larger and smaller. I'm going to calculate the magnification, calculate the image distance, and hopefully all my signs, they'll match up with this diagram, or this table right here and this table right here, and they'll match our cases. Then we're going to repeat for a convex mirror. So we're going to do 3 concave mirror examples and then 3 convex mirror examples. And we're going to start that in the next video, because I think I'm getting a little long-winded here. So a lot of stuff, a lot of cases that we have to memorize, a lot of rules that we have to follow. So I'll do these 6 different examples starting off in the next video. Okay, thanks.